0. A GPS satellite orbits at an altitude of this. Now, when they say altitude, what are they measuring that from? Sea level, the surface of the planet. Okay, so anytime you see altitude or height, remember, oh, if I'm thinking gravity, though, I've got to go center of mass to center of mass. So right away you should think, oh, I got to add the radius of the Earth to that. Oh, that's why they give it to me. And then also, oh, they're nasty here. They give you kilometers, and then the radius of the Earth in meters. So you got to make sure that you watch your unit. And they want to know what the speed of the satellite is. All right. So let's go here. 9.50. What does the path of a satellite look like? Like a circle. Like that's what orbit is using. You know, a lot of orbits are ellipses, but we'll consider that all orbits are circles just to make life easier. All right. So that's what I would put right away. Like the satellite travels in a circle. What do we know right away since it's traveling in a circle? It's accelerating which direction? Towards the middle. So, and what causes acceleration? This is one of those questions I'm going to keep asking. What? That's what acceleration describes, how the direction of the velocity is changing. But what causes that acceleration? Force, net force. Guys, this is something, maybe write it down 200 times or something. Net force causes acceleration. Like one of those base principles that we need to make sure that we have at our hand. So, and what is, so if I draw a little picture, here's my satellite. Well, let's draw a little bit. Here's the Earth. There's the path of my happy little satellite. And we said it must have a force on it in this direction. And that's actually going to be a centripetal force, right? Remember, centripetal just means pointing towards the center. What force would naturally be on that satellite that would be pointing towards the center of that circle? Gravity. So the force is gravity. And we could even go maybe one more step in here. Earth creates the field that makes the grav force. So Earth creates the field that makes the gravitational force. Any questions on the why before we dive into the how? This is kind of bringing together stuff from circular motion and gravity, right? So let's see. Probably be good to grab an equation that talks about one body making a gravitational field and the other one feeling a force. Oh, that's our gravitational. What? Let's see. Grab that. And paste it in. So in this case, Earth is creating the gravitational field. The satellite is in that field, and we have the radius. But we said that gravitational force is causing the circular motion because it's pointing towards the center. So we use Newton's second law. On this side, we have the gravitational force. On this side, we have the mass of the satellite and the acceleration centripetally. Remember, pointing towards the center there. So this side, if we expand a little bit, we have the mass of the satellite, big G. What's creating the field again? Right, so it's the mass of the Earth over. Now, if I think about my diagram here, I've got the radius of the Earth and with it, how far it is above the Earth. So those two things together, that's how big how far away the satellite is from the center of the Earth. So down here, I'm going to put radius of the Earth, and I'm going to call it h for the altitude, how high it is above the surface of the Earth. So I've got radius of the Earth plus the height above the surface of the altitude. And that's my gravitational force. Then I have the mass of my satellite, and for centripetal acceleration, if I remember back, I have v squared, how fast it's moving, over r, which is the same r because that's the radius of the circle also, right? V squared over r. That v squared over r is for my equation sheet again. Questions? I went on to my equation sheet. Remember, our equation sheet is our friend, right? And I looked up circular motion, our last unit, and acceleration centripetal is v squared over r being the radius of the circle. And so I substituted in for my acceleration centripetal here. Can I get rid of anything mathematically to make my life easier? Mass of the satellite. Anything else? One of the r plus h's. I can get rid of that square term and get rid of that one altogether. And so now, simplification-wise, I'm down to big G, mass of the Earth, over r, radius of the Earth, plus the altitude, equals v squared. Remember, I'm looking for the speed. And so, I could take the square root of both sides, couldn't I? That's convenient. So then I'd have the square root. And now here's where I need to start pulling values from my equation sheet. So I need the universal gravitational constant. That's right here, right? 6.67 times 10 to the negative 11. So 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Mass of the Earth. Wonder if that's on there. Oh, there it is. Mass Earth. 5.98 times 10 to the 24th kilograms. Okay. Radius of the Earth. Well, that was given to me in the problem, wasn't it? They want me to use 6.37 times 10 to the 6th meters. Plus the height above the planet, or the altitude, which for me is 2.04 times 10 to the 4th kilometers. Oh, there's just 1,000 meters in a kilometer, so that would just increase it by 3. So 2.04 times 10 to the 7th meters. I'll solve for V, you solve for V, see if we get it right. Because in my head I converted from kilometers to meters. All right, we're going to do 9.14. Gravitational force between two volleyball players is this. If the mass of the players are these amounts, what is their separation? Some people ask for 9.15. Same idea. They just give you, they leave out one other thing. And what we got going on here is that bodies with mass create a grav field thus attract any other body with mass. All right, so that's our Y. Oh, I wonder if we still have the equation in the clipboard. And really, both of these come down to making sure you're using the right units and you're plugging in. Now, would you guys mathematically be more comfortable if I plugged in all the values and then you mathematically rearranged it? Or do you want to mathematically rearrange it for the variable you're looking for and then plug in values? Which way works better for your math? Second one, rearrange it and then plug in. All right. So in this one, we're looking for their separation. We're looking for the R, how far apart their centers of mass are. So I'm going to rearrange this. I want to get the R by itself. So I'm going to bring it up, and I'm going to bring that FG down. So I'm bringing the R up and the FG down, I get R squared equals M1, big G, M2 over F sub G. Little cross multiplication, right? Remember, to cross the equal sign, all you have to do is the opposite function. So where everything's divided by R, I multiply both sides by R. Everything's multiplied by FG, I divide both sides by it. And then I do the square root. Square root of M1, big G, M2 over F sub G. I know M1. For me, it was 68. I know big G because I'm in this universe. I know M2. I think for mine it was 78. And then give me F sub G. So at this point, it's plugging in your values and seeing what you come up with for R. So give that a try. I'm going to plug in my values and then give it a try for me and see if I get it correct. So let's see. Make sure 68, 78. So. This is one of those places also, if you don't like using your exponent key on your calculator and you know, prefer doing times 10, caret this, where you also need to really be careful that the common math mistake would be doing the wrong division, wrong order in your division. So be cautious of that. If you get the wrong answer, check that you're not doing your math in the wrong order. All right, so we're moving on to Planet Cochran. Standing on a new planet, Planet Cochran. The planet has a mass of this and a radius of this. What's the gravitational field on the surface of the planet? Why must there be a gravitational field on the surface of the planet? Because it has mass. There you go. That's your main why. The planet has mass. It creates a grav field. And yeah. Let's grab our equation for creating a gravitational field, which is right here. And now we're going to put in our values. So I'm solving for the gravitational field strength, little g. Put in big G, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Put in the mass of my planet. For me, it's 5.375 times 10 to the 20th. 20th kilograms. And then the radius of my planet, which is 2.706 times 10 to the 5th. Meters. That quantity squared. I'm going to find out a value for little g and then check it. So you try it, I'll try it, and then we'll move on to part B. All right, so I got mine correct, which for me, my answer was 0.48968 newtons per kilogram. So that's, I've been forgetting to box my answers this morning. That's part A. And then in part B, now that I've answered that, they want, if the mass is this, what's your weight on planet Cochran? Well, if we look back to our handy-dandy equation sheet, you should notice that within the brackets are the field, and then the weight is just the gravitational force. So it's just our answer from part A multiplied by the mass. Remember, in this little bracket is little g, what we've been using all along as the gravitational field strength. So I'm just going to take, for part B here, F sub g equals, and I'm going to use the truncated formula of it, mg, and just substitute in. 133 kilograms, I think it is. Times, for me, 0.48968 newtons per kilogram. That's right? 133, yep. And that will be the weight that I figure out. Newton, 65, for For me, 65.1 newtons. See if I got it right. All right, so we're going to go with mountain G here. We only have a few minutes left, so I'll try to do this under 5 minutes. Very similar in a sense to the satellite one, in that the Earth is creating the gravitational field, and we're looking at, now that we're a height above the surface, how much has it diminished? All right, you guys remember, just a little bit quieter so I can hear myself, if you don't mind. So mountain G and Earth makes field and, oops, I have the interesting form. Let's, nice. I'm using my same equation. One thing to remember is, if you look at the diagram here, the radius, remember, what we care about is how far we are from the center of mass of the thing creating the field. So it's not how high we are above the surface, but how far we are from the center of the Earth, which is its center of mass. So our height, our radius from the middle center of mass of the Earth is the radius of the Earth plus the height above the surface. So my height is 3250 meters. So in my gravitational field here, big G, I'm going to have big G, 6.67 times 10 to the negative 11 Newton kilograms squared per meter squared. Reverse that. But mass of the Earth, handy dandy equation sheet again. Get the mass of my Earth, 5.98 times 10 to the 24th kilograms. I am the radius, remember this RP is going to be the radius of the Earth plus the height above it, like it was for the GPS satellite, the first one we started with. So take the radius of my Earth, 6.38 or 6.38 million meters plus 3250, and don't get to square that. And you will, let's check it. You get the correct answer.